Dear girls, in this session we are going to see silicon and insulator technology. This is the latest compared to previous technologies. We have seen previously CMOS technology, then bipolar technology, then BiCMOS technologies. So in all these three technologies, we have seen that a substrate is a basic material above which other components would be layered. Whether you consider CMOS technology, substrate above which then we have seen P-well, N-well, then PMOS construction, NMOS construction was happened. So substrate is a major component in order to form the any component, any other components above which above on the substrate. So in order to separate these components, PMOS or NMOS or PNP or NPN like that, when the separation is happening, the traditional separation method was used as isolation method was used as dielectrically isolation DI processing. So this dielectrically isolation is the material which is connected between one component to other component, given a polarity or the given a potential in such a way that the two components would be separated with a potential. So that is what dielectrically isolated. The materials are doped or taken in between the components. The material would be taken in such a way that there would not be any contact to be formed in such a way that they have taken the formation of the material in between the components. So that's what dielectrically isolated process was used traditionally. But the main purpose is to use this dielectrically isolated is for the separation of the charge that is generated between the components. The PMOS to NMOS separation should be happen if the charge is accumulated unknowingly or unnecessarily. There would be charge transformation from PMOS to NMOS, which is not required operation. So that's why to reduce the charge generation in the substrate and to obtain radiation hardness for military and space applications, the process traditionally was used as dielectrically isolated processing. So actually there is a problem called latch up. It was observed in CMOS technology. So when there is a short circuit path is created over a period of application of voltage. So from VSS to VDD, if the path is created, short circuit path is created, unnecessary current would flow from PMOS to NMOS. That was not required current apart from the required operation. So the actual operation will go erroneous in the case of CMOS technology. So here, to avoid this one, silicon and insulator technology have come up with a substrate that is that was amount of work was done on this silicon and insulator using a sapphire for both substrate and insulator. So generally, silicon and insulator prior to the CMOS was used as substrate, silicon substrate, above with silicon dioxide as an insulator. But in this case, silicon and insulator, silicon is the basic material substrate, sapphire for both substrate and insulator. So silicon, apart from that silicon, sapphire as well as insulator. The sapphire was used as a substrate as well as insulator. So this technology was called as silicon and sapphire or silicon and substrate. So here, this is it is a restricted version of the silicon and insulator technology. The enhanced device performance SOI device structure results from the reduced parasitic substrate capacitance. So when we use sapphire material, so parasitic elements which are resistance or capacitance would be reduced such that the performance will be improved in terms of radiation hardness will be improved, and the charge generation also between the components charge generation also reduces. That was performance improvement we can observe in silicon on substrate technology. So compared to silicon and substrate technology, another one extended version of that SOS, we can see SY technology, that is small islets of silicon are formed on the insulator film. So substrate above which silicon on insulator. So above the substrate, we can see some insulating materials like a island. So that means some small portions of insulating material can be observed on the silicon substrate. That's what silicon and insulator technology. Small islands of silicon are formed on an insulator film. So this SY fabrication process coupled with lateral isolation. So between the individual components, P mass or N mass or any other components are layered above the substrate. These components will be separated or isolated using these insulator films. That's what lateral isolation, because above the layer itself is the formation of a component. So lateral isolation, that means the top layer is taking the component formation. That layer top layer is having the isolations among the components, among the small units, the P mass or N mass, whatever the units we consider. So that's why lateral isolation technique, this will be called as lateral isolation technique. So, and the advantage of this lateral isolation technique is completely the latch up condition or latch up problem is eliminated in this SOI. That means the formation of a short circuit path between VSS and VDD are eliminated due to this isolation portions. So this is latch of free circuits. It is become like a latch of free circuit, and there is no parasitic PN parts also within the substrate, and also SY films can be made extremely very thin. The another advantage is very SY films are made very thin. That is an advantage. So due to this advantage, fully depleted MOSFETs can be observed. So fully depleted MOSFETs are essential in order to see the amount of current that required to flow within the mass transistor is more, as well as with less application of voltage. So it is very speedy, as less application of voltage is essential. As the voltage application is reduced in this kind of SOI, so it will be very speedy device. It becomes a very speedy device and operated at a high speed of frequencies like 2 gigahertz. And the thin film SY CMOS devices and circuits have reduced short channel effects. So this is one of the difficult or issue seen in CMOS fabrication. As the channel length is reduced technology node to other technology node, there would be issue of short channel effect. A short channel in the sense, the channel as it is shrinking, the depletion layers as between source and drains would come closer, indicates an error of punch through, or required amount of current would flow more current compared to required current. It flows due to breakdown. So all these comes under short channel effects. So that short channel effect will be reduced in this SOI technology, and reduced hard electron generation also. So as in the CMOS case, we need to make the device on, we need to spend more voltage on the gate, or the device potential. But in the case of SOI, because of the construction, with a small amount of input application of voltage, the device will go into operation. So it reduces hard carrier effect also. And it's also another advantage is sharper subthreshold slopes. So the subthreshold slope, that is between voltage or current, subthreshold leaky currents will be very reduced in a manner of sharper down manner. So that is another advantage. And because of the relatively low wafer yield problems, so the yield, as issues are very eliminated or reduced, yield also improved. So the major market concentration is on SY chips in military as well as aerospace applications. So the real impact of SY technology on the commercial market is expected to occur in the manufacturing of submicron devices, 0.25 micron meter level. So compared to zero point 0.5, in the previous section we discussed about zero point 0.5 or 0.55, 0.6 micron meter technology node. So SY can be reached up to technology nodes of 0.25 micron meter. That is essential. As the technology reduces, we can see more number of cells can be incorporated, density would be increases. So since at this point the production cost for bulky API wafers will be greater or equivalent to the SY wafers. So even at this technology node, whatever the construction is happened at SY wafers, the same cost is affecting with the technology node when it goes to 0.25 micron meter technology. So people are taking this as an advantage to construct the chips or ICs at this technology node. Then some of the important SY technologies used to produce a starting material include. So what are the basic materials that are required to produce SY technology? If you observe that, there are a couple of materials like Separation by implanted oxygen, shortly SIMOX. S stands for separation, IM stands for implanted, OX stands for oxygen. So separation by implanted oxygen, that is one material. So as we mentioned previously that between components we require isolation islands. So these isolation islands can happen using oxygen. So this is one material that we can use for implanting between the components PMOS or NMOS or any other component in the on the chip layer, so that the implantation can happen through this oxygen. So that is one point. Then zone melt recrystallization. So this is one more process, that is where crystal can be wherever it is required. So there the process can be taken in such a way that at that local point recrystallization happens using some certain temperature, so that the crystal can be locally formed at that point itself, so that zone melt at that zone itself we can use it, zone melt recrystallization. Then full isolation by porous oxidized silicon. So this is another technique that is incorporated in SY. So that is full isolation by porous oxidized silicon. So in the silicon again there is kind of material like full isolation using porous oxidized. So that oxidized silicon is having some porosity such that wherever it is required to incorporate between the components, between the layered components, so that it is easily absorbable with the base substrate and other materials. So that's why it is full isolation using porous oxidized silicon is another technique. Then epitaxial lateral growth. Epitaxial lateral growth is another technique, that is after substrate silicon and insulator substrate formed, one thin layer of epitaxial growth can be taken for separation of the separation process is made easy to form between the components. Then another one is vapor bonding and etchback. Vapor bonding and etchback, that is a modified DI process that was observed in silicon and sapphire SOS process. So these are all different techniques which are essential for SOI technologies to form. These are the starting materials to be used. So, the separation by implanted oxygen is the most commonly used technique and requires a high dose of oxygen. High dose of oxygen can be represented as O minus ions, O negative ions, which provides a minimum concentration necessary to form a continuous layer of SiO2. So high concentration of oxygen will be taken, and it is formed above this SiO2 as a continuous layer. Then the energy of the implant must be high enough to enough so that the peak of the implant is sufficiently deep within the silicon, zero point 0.3 to zero point 0.5 micrometer technology. So whatever the implant it is taking, the implant should be with force. We have to with force enough force we have to use that implant such that high energy is required to have this zero point 0.3 to zero point 0.5 micrometer depth. So implantation is happen with that high force. That is zero point 0.3 to zero point 0.5 micrometer depth is required. Then wafer is normally heated about 400 degrees centigrade during the implantation process. So during that implantation process, as this temperature, this much of temperature is essential in order to see the dopants properly sit in the wafer. So that's why this much of temperature is essential during the implantation process to ensure that the surface maintains crystallinity during the high implantation dose. Then a post-implant anneal is performed in neutral ambient N2 or helium for a sufficient time, that is 3 to 5 hours. So after implantation takes place, it is post-implantation process is a neutral ambient N2. So nitrogen or helium can be used till 3 to 5 hours to be taken at the temperature range of 1100 to 1175 degrees centigrade. So this is the process where it is required to have a buried layer, that is a deep SiO2 layer, buried layer is required to essentially to form. For that the process will take 3 to 5 hours time. and even at high temperature also. And finally, the annealing. Actually, this step is annealing step, is also allows excess oxygen to out diffuse, so thereby increasing the dielectric strength of the buried oxide layer. So due to this SiO2 buried layer, the advantage of having this buried layer is having strengthen buried oxide layer. Then after the annealing step, the crystallization silicon surface layer is typically only 100 to 300 nanometer thick is formed. So therefore, an additional layer of epitaxial silicon is deposited so that single crystal regions 0.5 micrometer are available for the fabrication. So after buried layer, a single epitaxial layer would be taken. That is the final step in order to incorporate different components on this epitaxial layer. So this is what silicon and insulator process till now we have seen, which requires, so these are the different kind of materials, and to form the silicon and insulator with high doses of oxygen, as well as implantation at a required temperature, and post annealing temperature, in order to have a buried layer. All these steps are essential for silicon and insulator process.